Welcome to the deep dive. We're here to cut through the noise, sift through a whole stack of sources, and really pull out the insights that help you get truly well informed. Today, we are diving headfirst into something that's, well, it's everywhere: artificial intelligence and machine learning. You see it on your phone, maybe in self driving cars. It's talked about constantly. Lots of buzz, lots of complexity. Sometimes it just feels like magic, right? So, our mission today is to demystify it. We want to give you a solid grasp of what these technologies really are, how they actually work deep down, and what the leading experts are thinking about the future. We've looked at a ton of stuff, foundational texts, insights from the big names in the field. Get ready for hopefully some surprises and maybe a few aha moments.
Absolutely. And it's such a critical area to understand because, well, it's filled with these incredible advances, but also, frankly, quite a few misconceptions. Often, the public idea of AI doesn't quite match the, let's say, the nuanced reality. So this deep dive should really help you navigate all that with more clarity. We're aiming to show the mechanics, not just the marvels.
Okay, great. Let's unpack this right away. Machine learning. We hear that machines program themselves. What does that actually mean? How's it different from old school programming where you write every single line of code?
Yeah, that's a perfect starting point
Yeah.
because it is a fundamental shift. Think about it like this. Traditional programming, you give the computer very explicit rules. You say, if this happens, do that.
Mhm.
With machine learning, you give the computer data, lots of data, and examples of the outcomes you want.
Mm.
And it learns the rules itself from that data. The most common approach here is something called supervised learning.
Supervised learning, okay. What's the core idea there?
Well, what's fascinating is how powerful it is, despite its conceptual simplicity. Imagine you want to teach a machine to spot spam emails. Instead of trying to write millions of complex rules like, if it mentions Nigerian prince, mark is spam, which is brittle, right?
Yeah, spammers would just change the words.
Exactly. So instead, you feed the machine a huge data set of emails that humans have already labeled spam, not spam. For each email, the machine looks at its characteristics.
Mhm.
Who sent it, the subject, the words used, maybe how many exclamation points. We call these characteristics a feature vector. It's essentially a list of numbers that represents the email's traits.
Okay, so the feature vector is just translating the real world thing, the email, into numbers the computer can crunch.
Precisely. And once the machine has these feature vectors, and their labels spam, not spam, it starts building what we call a model. The model is basically a mathematical function. It tries to predict the label for new emails it hasn't seen before.
Mhm.
And the machine keeps adjusting the internal numbers, the parameters, within that function. It's solving what's called an optimization problem. Basically, it learns from mistakes, tweaking itself to get better and better at predicting correctly. And this same basic idea applies to predicting stock prices or diagnosing diseases from medical scans or countless other things.
Right. But here's where it gets, well, even more interesting for me. The big revolution lately seems to be deep learning. How does deep learning build on that? What makes these deep neural networks so much more powerful?
Yeah, deep learning is where a lot of the recent excitement comes from. It's mostly powered by these deep neural networks. Now, these are software systems inspired by the brain, but definitely not exact copies. Think of them like incredibly complex electrical circuits, but made of software units arranged in many layers, like a multi-layered cake. Each unit in a layer takes inputs from units in the layer below it. These inputs are weighted. Some are more important than others. The unit does a simple calculation on these weighted inputs and then passes the result through something called a nonlinear activation function before sending it on to the next layer.
Okay, nonlinear activation function. That sounds technical. Why nonlinear? What does that do?
That's a really key point. If everything was linear, if these functions just produce straight lines, then no matter how many layers you stacked up, the whole network could only learn simple straight line relationships in the data.
Like drawing a straight line through points on a graph.
Exactly. But the real world, real data, it's almost never that simple. It's messy, complex, full of curves. Nonlinear means the function can introduce bends, curves, complexities. It allows the network as a whole to approximate incredibly intricate, wiggly functions. It's like giving a sculptor flexible clay instead of just rigid blocks. This lets them tackle problems like recognizing subtle visual patterns or understanding language nuances things linear models just can't handle. And the learning part, where it adjusts all those internal weights, that often uses an algorithm called backpropagation. This is a massive breakthrough. It's a clever way for the network to figure out how much each connection, each weight, contributed to any errors in its prediction, and then efficiently adjust all those weights, layer by layer, going backward from the error. Honestly, without backpropagation, treating these really deep networks would be computationally infeasible. Modern deep learning just wouldn't be practical.
That is a huge piece of the puzzle, that one algorithm enabling so much. Okay, so speaking of enabling things, we see AI doing amazing stuff now. Facial recognition, real-time translation, beating world champions at Go. Can you walk us through some of these big successes? How do they actually work under the hood?
Absolutely. The progress has been, well, pretty staggering in some areas. Take image recognition. A
Yeah.
huge leap forward came from combining convolutional neural networks, or ConVNets, with the arrival of truly big data. You had researchers like Fei-Fei Lai leading projects like ImageNet. This created enormous data sets, think over 1 million images, all meticulously labeled across 1,000 different categories, like cat, dog, car, chair.
Wow.
Yeah. And ConVNets are specifically designed for image data. They process images in layers, learning hierarchies of features. So the early layers might detect simple things like edges or corners. Later layers combine those into more complex shapes. And deeper layers still might recognize object parts or even whole objects like faces. This ability to learn directly from vast amounts of visual data, it completely transformed computer vision.
Okay, and what about games? Beating the Go champion was a huge deal. How did that work? Was it just massive computing power?
Not just power, though that helped. That success mainly came from reinforcement learning. Here, the AI doesn't get labeled examples like in supervised learning. Instead, it learns by doing. An AI agent performs actions within a simulated environment, like making a move in Go, and it receives feedback, rewards or penalties based on the outcome. Did that move help it win?
Like training a dog with treats?
Sort of, yeah. For games like Go or old Atari games, the system basically just plays against itself or explores the game, trying out different moves and sequences. It gradually learns which actions, in which situations, tend to lead to higher rewards, meaning winning the game. Now, for something really complex like driving a car, you can't just make a giant list of every possible situation and the best action at Q table. The number of states is practically infinite.
Right.
So instead, these systems use neural networks to estimate the potential value or reward of taking certain actions in a given state. AlphaGo, for instance, the AI that beat the Go champions, used this approach. It played millions and millions of games against itself. It used a clever technique, sometimes called learn a guess from a better guess, to continually refine its strategy, its estimations, until it became better than any human player. It wasn't programmed with Go strategies, it discovered them.
Incredible. Learning by playing, essentially, and language. Understanding and generating text seems so uniquely human. How's AI doing there?
That falls under natural language processing, or NLP. And neural networks have made huge strides here too. Machine translation, for example. Companies like Google, Microsoft, they've seen massive improvements in quality, really bridging the gap compared to older statistical methods. It's often surprisingly fluent now. We also see AI used for sentiment analysis, figuring out the emotional tone in text. Is this product review positive or negative? Really useful for businesses. And another really fascinating area is word embeddings, like the famous Word2Vec model. The idea is to represent each word not as a simple token, but as a vector, a list of numbers in a high-dimensional space. And words with similar meanings or that appear in similar contexts end up being close to each other in this space. Cat and dog would be closer than cat and car.
Okay.
But what's really cool is that you can do math with these vectors. The classic example is if you take the vector for king, subtract the vector for man, and then add the vector for woman.
What happened?
You get a vector that's incredibly close to the vector for queen. Yeah. It shows the network isn't just memorizing definitions. It's actually capturing semantic relationships, analogies, within the structure of language itself. Pretty amazing.
Okay, those are some genuinely remarkable achievements. AI really can do some incredible things. But let's step back. Where does it still fall short? What are the limits of these systems, even the really powerful ones? And what does that tell us about the dream of, true human-level AI or AGI?
That's the crucial counterbalance, isn't it? Despite all the progress, current AI has very real, very significant limitations. First off, there's the problem of generalization and overfitting. Models can get too good at the specific data they were trained on. They essentially memorize the training set, including its quirks and noise, instead of learning the underlying general principles.
Like cramming for a test versus actually understanding the material.
Exactly like that. So an image recognizer trained mostly on photos with blurry backgrounds might fail completely if you showed a similar object against a sharp, clear background. Or think about a game-playing AI. It might achieve superhuman skill in the standard game environment. But if you change something tiny, like shift the position of a paddle by just a few pixels, its performance can suddenly plummet. It shows these systems often learn very specific tricks or correlations tied to the training data, not a robust, flexible understanding of the task itself.
So it's brittle, highly optimized for one thing, but breaks easily if things change slightly.
Very much so. And that connects to the second big limit, a fundamental lack of common sense and abstraction. Current deep learning systems are, frankly, terrible at genuine understanding, common sense reasoning, and seeing abstract patterns the way humans do. You mentioned speech recognition confusing moose, the dessert, with moose, the animal. That's a classic example. It lacks the real-world context to know which one makes sense.
Right.
Or consider something called Bongard problems. These are visual puzzles. You get, say, 6 diagrams that follow some abstract rule and 6 that don't. You have to figure out the rule. Humans usually get these quite easily, even with just those 12 examples, by grasping the underlying abstract concept. But even state-of-the-art contents find these incredibly difficult. They might need tens of thousands of examples and still struggle to generalize the abstract pattern. It strongly suggests that these systems lack the kind of innate cognitive structures, intuitive physics, basic psychology, the ability to form abstract concepts quickly that even human babies seem to possess. They don't build a model of how the world works.
That difference between sophisticated pattern matching and actual world understanding seems like a huge gap. And what about those adversarial examples? That sounds worrying.
It is, yes. It's a major vulnerability and security concern. Adversarial examples are inputs that have been slightly, often undetectably, modified to fool an AI system. You can add tiny, carefully crafted noise patterns to an image pixels a human wouldn't even notice and cause the system to misclassify it completely, often with very high confidence.
Like making it see a stop sign as a speed limit sign.
Exactly that kind of thing. Or tricking facial recognition with specially designed glasses. Or even subtly altering a medical scan image to make it look like there's a tumor when there isn't, or vice versa. It really highlights how different their seeing is from ours, and how fragile their performance can be when faced with inputs designed to deceive them.
Okay, so given these big limitations, the brittleness, lack of common sense, vulnerability, what does this mean for AGI? Artificial General Intelligence. The idea of AI that can do anything a human intellect can, is it close? Far away?
Well, that's the million-dollar question, isn't it? And the predictions are all over the map. You have figures like Ray Kurzweil, who are very optimistic, predicting dates like 2029. Then you have others like roboticist Rodney Brooks, suggesting maybe 2200 or even later. Yoshua Bengio, one of the pioneers of deep learning, uses a really good metaphor. He says it's like we've been climbing this tall hill with deep learning, making amazing progress. But as we get near the top of this hill, we look out and see a whole range of other, much bigger hills in the distance.
Hills like common sense. Extraction.
Exactly, those fundamental cognitive abilities. And many experts, including Geoffrey Hinton, another giant in the field, are skeptical about the idea of a single, general-purpose AI like Commander Data emerging anytime soon. The general feeling among many researchers is that while recent progress is impressive, getting to true AGI likely requires more fundamental breakthroughs, new ideas, not just bigger versions of what we have now. We're likely still a long way off.
That makes sense. It's not just about more data or faster computers, it's about missing ingredients. So shifting gears slightly, beyond the technical side, AI obviously has huge societal implications.
Yeah.
What are the thoughts on jobs, bias, regulation, control? These are things people worry about a lot.
They are, and rightly so. Let's take job impact. The general consensus from research isn't necessarily mass unemployment, but significant change. Yes, many repetitive, predictable tasks, things where humans have essentially acted like biological robots, will likely be automated. Data entry, certain types of assembly line work, maybe some basic analysis. But history suggests new technologies also create new kinds of jobs. So the net effect might even be job growth. But it absolutely requires major shifts in skills, significant retraining, and embracing lifelong learning. It's less about high skill versus low skill, and more about routine versus non-routine adaptable tasks.
And bias. We hear about AI systems showing racial or gender bias.
That's a critical ethical issue.
Yeah.
And the key thing to understand is that the bias doesn't usually come from the AI algorithm itself being malicious. It comes from the data we train it on. If the historical data used to train a loan application AI reflects past societal biases, where certain groups were unfairly denied loans, the AI will learn and unfortunately perpetuate those biases. Garbage in, garbage out, essentially.
So fixing the data is crucial.
Fixing the data, being aware of potential biases, auditing the systems, it's a complex challenge involving technology, ethics, and societal awareness.
What about regulation? Should we be regulating AI research?
Most experts tend to agree that regulating the applications of AI makes sense. much like we regulate drugs or cars or airplanes, to ensure safety and efficacy, not necessarily regulating the fundamental research itself, which could stifle innovation. So, rules around how self-driving cars are tested and deployed, or standards for medical diagnostic AI, or crucially, strong international norms and potentially treaties around autonomous weapons. The idea of weapons that can select and engage targets without human intervention raises profound ethical questions about accountability and the value of human life. Their potential scalability is also a serious concern. These are active, difficult debates.
And finally, that big long-term fear, the control problem or value alignment. Ensuring superintelligence, if it arrives, is actually good for us.
Right, this is the idea. If we eventually create AI far more intelligent than ourselves, how do we make sure its goals are aligned with human values and well-being? Opinions here really diverge. You have people like Andrew Ng who argue it's premature, like worrying about overpopulation on Mars before we've even landed there. Focus on the current problems like bias and jobs. Then you have thinkers like Nick Bostrom who see it as a potentially huge existential risk. A superintelligence optimizing for some seemingly harmless goal, like making paperclips, could theoretically convert the entire planet into paperclips if its values weren't perfectly aligned with ours from the start.
That sounds like science fiction, but the logic is unsettling.
It is. And then you have optimists like Ray Kurzweil who see AI more as tools that will augment humanity, extending our reach, and believe technology historically trends towards greater peace and cooperation, despite challenges. So it's a very active debate with smart people on all sides looking at that very long-term horizon.
Wow, okay. What a journey we've taken. From the basic math of learning patterns, through these incredible feats in vision and games, all the way to the deep challenges of common sense, ethics, bias, and these really profound questions about the future of intelligence itself. It's so clear that AI isn't one single thing. It's not magic. It's this incredibly complex, fast-moving field. Huge potential, yes, but also really significant hurdles and questions we need to grapple with.
Exactly. I think if there's one key takeaway, it's to look beyond the hype, beyond the simple stories. Appreciate the current power, absolutely, but also understand the very real limitations. And remember, AI learns from the data we provide. It's an incredibly powerful tool, yes, but how it develops, how it's used responsibly, that ultimately come down to human choices, human values, and ongoing critical thinking.
So that brings it back to you. As these systems weave themselves more and more into our daily lives, into our society, how do you see our role evolving alongside them? How do we build a future where this partnership between human intelligence and artificial intelligence truly benefits everyone? Something to think about. Let that curiosity drive your own deep dive.